Welcome to the solution to homework set number 1 for ECE 320 for spring 2022. The first problem is resistors in series and parallel. At DC, capacitors don't matter. Impedance of capacitor is 1 over j omega c. This is infinity, meaning the current is 0. You don't have to worry about zero current, so basically ignore these. I want to find out what's the resistance between A and B. So that's 35 in series with 400. In series, all the current through R1 passes through R2, so those are in series. In parallel, the voltage on one side is the voltage same as the voltage on the other side, so these are in parallel. To do that, I like using an HP calculator. I'm going to show you that. I've got 435 ohms, so there's 435, in parallel with 300. In parallel, the inverses add, so I take the inverse of R1, inverse of R2, add the inverses, take the inverse. This is 177.551 ohms. In series with 25, in series they add. In parallel with 200, that's 1 over R1, R2, 1 over R2, the inverses add. This is 100.634 ohms plus 15. So there's the answer, 115.634. Problem 2. Assume x equals minus j100. Now repeat. How do I want to do this? Let's put this over here. I've got 400 in parallel with minus j100. So on this calculator, I do 400 in parallel, means the inverse, minus j100. The way you input complex numbers on this calculator is the complex. We'll do 0, enter, negative 100, complex. So there's 0 minus j100. Take the inverse, inverses add. These two together gives you 23 minus j94. In series with 35, in series they add. In parallel the inverses add. So take the inverse of all this, plus the inverse of 300. There's 300, inverse, add. Plus the inverse of minus j100. Here's 0, enter, 100, negative, complex. There's minus j100. Take the inverse, add, inverse. So all this is 21 minus j46 ohms. In series with 25, in series they add. In parallel with 200, take the inverse, 200, inverse. In parallel with minus j100, 0, enter, 100, negative, complex, negative j100, inverse, add. Take the inverse. This is all 23 minus j30 ohms plus 15. So problem 2, the answer is 38 minus j30. That's kind of how you use the Sp22 calculator. Voltage nodes. With voltage nodes, I've got 3 nodes. I need 3 equations for 3 unknowns. Start with the easy ones. I know that from the voltage source, V3 minus V2 is 20. That's one equation. I need 2 more. At node 1, I can do the current down, current right, current up equals 0. Current down is V1 over 250 minus 15 milliamps plus V1 minus V3 over 150. I need 1 more equation. I can't do the equation V2 because I don't know what this current is. I can't do the equation V3. I don't know that current. That's where supernode comes in. Now if you kind of mark off the ones that I've already included, I've included the voltage source, so that one's good. I've included the 250 ohm, the 15 milliamp, the 150 ohm. The 350, 450, and 200, they do matter. They need to appear in your equation somewhere. The supernode has to include these resistors and be an equation I can write. So if I do a closed path like this guy, I can find the current from that supernode. It's going to be the current through the 250 ohm resistor, right here, plus the current through the 350 ohm, plus the current through the 450 ohm, plus the current through the 200 ohm. And that's everybody. I've got 4 elements attached to the supernode. I've got 4 terms. That's my 3 equations, 3 unknowns. To solve, group the terms, put in matrix form. For example, the first equation is B3 minus B2 is 20. Second equation, that times B1 minus this times B3 is 15 milliamps, and so on. Throw it in MATLAB and solve. Here I've got A times B is B. Or the voltage is the inverse of A times B. In Circuit Lab, I can build that circuit. It's just drag and drop. In Circuit Lab, what Circuit Lab looks like, I can say here's my voltage source, here's a resistor, here's ground. Connect them all together. Double click when I change it, 10 volts. When you're done, it'll look like this. If I go under, I can't see it. Yeah, come back. On the screen, come back. It's trying to tell me what I want to do. I don't want to do that. I want to do this. I can go under Simulate and do a DC solver. Solve for DC. I'll add expression. In this case, I'll add V1, V2, V3, and solve. It comes up with this answer. Exactly the same thing that I calculated. Test voltage nodes. Current loops. What I do is I've got 4 windows. I'll define 4 loops. I like making them all go the same direction, all going clockwise. The voltage around each loop's got to add to 0. So I need 4 equations for 4 unknowns. Let's start with the easy one. The current source says that this current is 15 milliamps. That's I1 minus I2. Now start going around loops. This loop I can't do because I don't know the voltage across the current source. I2 I can't do. I can do I3. All these voltages have to add to 0. So 350 times I3 minus I2 minus 20 plus 450 I3 minus I4 equals 0. Let's subtract 20 because I hit the minus sign first. Loop I4 I can write. That'll be 450 I4 minus I3 plus 200 I4 equals 0. I need one more equation. And if I look at it, I've got the 15 milliamp. That's been written in the equation. 350 is in there, 20 is in there, 450 is in there, 200 is in there. My super loop has to include the 250, 150 ohm resistors. So here's one candidate. And that equation would just be 250 I2 plus 150 I1 plus 200 I4 equals 0. Back where I started. 4 equations for unknowns. To solve, group the terms, put in matrix form, throw in MATLAB, solve, and here's the currents. If I do that in Circuit Lab, what I can do, well, in Circuit Lab, if I click on the left side of a resistor, like right here, they'll tell me the current through that resistor. So doing the same thing up on this circuit, I want to know the current through this resistor. That'll give you I1. I can click on this right here. That'll give me the current through R2. That's I2. I3 is hard to get. Across R5, that'll give me the current I4. And if I1, I2, here's I2, and I4, that's this guy, are all correct, it's probably the right answer. The last problem is superposition. I've got 2 terms, a DC and an AC term at the input. I'll have 2 terms at the output, a DC and an AC term. Start at DC. When Vn is 10, this doesn't matter, that doesn't matter. I just have a voltage divider. 100 over 100 plus 15 times 10, 8.696 volts. That's the DC term for V2. Now do the AC term. For AC, the frequency is 450 radians per second. So the inductor becomes J omega L, J377 ohms. The capacitor becomes 1 over J omega C, which is minus J27 ohms. Put these in parallel, I get 7.1 minus J25. Again, that's going to be 1 over R1 plus 1 over R2 inverse, gives you a complex number. And Vn is actually 6 minus J4. The real part's cosine, that's right here, minus J is sine. I can now use voltage division. It's Z2 over Z2 plus Z1 times Vn, complex numbers, but it's just a voltage divider. And you get a complex number. What that means is the real part's cosine minus J is sine, or in polar form, there's the amplitude, there's the phase shift. If I check in Circuit Lab, build this circuit, the input, well, Vn is 6 minus J4, in polar form, 7.2 at minus 33 degrees. So there's the amplitude, 7.2 volts. Minus 33 degrees. Circuit Lab actually uses a sine reference. This is the phasor form for cosine, shift by 90 degrees. Here's the phasor form for sine. There's my phase shift. So these together gives you 6 minus J4 in Circuit Lab. Build a circuit and do a transient response. So over here, I'll do a time domain and have it go for a couple cycles. And that's what it looks like. So here's your input. There's the output. Define V2. I'll take the maximum and the minimum. The difference in the two is 8.694 volts. That's the peak-to-peak voltage. Oh, that's the DC voltage. That's the average of the two. And I calculate 8.696, about the same. The AC voltage is take the difference in the two. That's the voltage with units of peak-to-peak. Again, so if we have a sine wave, this distance right here is peak-to-peak. Divided by 2, that's the peak voltage. That's what this is. We get 0.616 volts peak. And if we want RMS, that's the peak divided by square root of 2. What we calculate was the peak voltage. I calculated 0.616. That matches up with Circuit Lab. There's also a phase shift. This peak is delayed from that peak. That phase shift is the difference between V1 and V2 in angle. And this is one cycle, 360 degrees. This is 180 degrees. And it looks like it's a little bit less than 180. Let's say maybe 170 degrees. If you convert it, V2 is delayed by 160 degrees from V1, a little bit less than 180. But it should check out. Normally just look at the amplitude. Phase also does show up, but amplitude is a lot easier to see, and oftentimes that's all you care about. So that's homework number 2, or homework number 1 for ECE 320 for spring 22.